Welcome back. Yesterday, day before yesterday, we started with the quantum Hall effect. I think we saw its experimental beginnings, somewhat vague terms that there are various ways to understand the effect, so that the current that starts flowing could be flowing in the bulk of the sample, could be flowing just on the edge of the sample, or there is this idea of the laughing pump. Actually, I brought something. Here once again. So there was also the idea of the laughing pump as an explanation of the quantum Hall effect, and in particular the quantization of the quantum Hall component. Today we return to that and see it somewhat more mathematically, or for definitions and how the different definitions would be related. Then what we also saw days ago was that quantum Hall effect was just an example in a much wider class of topological insulators, and that it could occur not just in dimension 2, but it could occur under the protection of particular symmetries as well. And then different quantities would be quantized or would serve as index. And here is the overview. And what we had from the quantum Hall effect is just we see here. Then I promised that we would look in particular some other special cases later on. But, given some time constraint, I changed my choice. So we will later today see this class A2, which enjoys the time reversal symmetry theta, which is odd, and no further symmetry. In 2 dimensions, it should give rise to an index C2 rather than to an index C as in the quantum Hall. And tomorrow, I would like to go to this class here, D, but we have particle Hall symmetry, because this has become somewhat topical, called Majorana fermions, and they're supposed to be a candidate for a quantum computer. So I should like to explain why topological, kind of topological matter could serve that. Okay, but first things first, let's turn back to the quantum Hall effect and go towards mathematics. We saw already a few things, so that we want to look at single particle operators on the lattice typically being C2, and you can hop from one side x to a nearby side x prime. That is described by, so to speak, an infinite matrix, more properly the Hamiltonian, which has matrix elements HP x prime x. So this describes the hopping amplitude for x groups. And they are short range, so this is non-zero, only if the 2 lattice sides x and x prime are very close. Okay, so I think this can be skipped. So there was this distinction between spectral gap and mobility gap. And then we had observables, generally called x. And what is important is the rate of change of x, which is given by its commutator with the Hamilton. So if x is the charge, it's some region of space, then let's see is the rate of change, so it is the current going in or out of that. Another thing was the single particle density matrix, which is called Rho. It tells us how single particle, so we have many body state, but there's a single particle marginal of density matrix called Rho. It's a commission operator between 0 and 1 that has to be dispersed. It tells us about any single particle state, the degree of occupancy it has, and that must be between 0 and 1. And then if you have an observable x, and you want to know what is the single particle observable, many particles they can, many particles they contribute to that observable. How much it contributes can be inferred by just knowing the single particle density matrix of that manifold state. All you've got to do to take your observable X, multiply this with the single particle density matrix. So, and take the base of the problem. The last thing was just about gauge transformations in electrodynamics, which will come up next. So you have vector and scalar potential, say phi, but the A will play a role. And you can change it by a gauge transformation. So if you say before, it becomes a time variable gradient of any function of space and time. Okay. In particular, look at functions of space alone. That doesn't change the magnetic field because the curl of what you add with is a gradient, curl of the gradients. Now, if you had no A field before, therefore no B field, by changing this thing, just having a gradient, new A prime just being a gradient, would still give no B. That's called a situation of a pure gauge. B field, there's no B field of its own. It's just the gauge transformation, and this gives E equals C. And then in quantum mechanics, Hamilton's out of that form, say the continuum, something similar in the exactly which we have seen, but never mind. If you do a gauge transformation, that also affects the quantum state of your part. So if the wave functions psi of x before, then gets multiplied by e to the ik of x. That is how it acts as a gauge transformation. In the multiplication by e to the ik of x, it's the unitary operator, also multiplication of cost, and the h changes to this new Hamilton h prime by unitary conjugation is the h. That is to be kept in mind. And with that, we can understand first understand what is the Loftin idea of the transport by the pump, and then why this has something to do with the bulk interpolation. So, I don't have the picture handy, but you can remember it, because a ribbon, take a ribbon, and this is your sample, and then in addition to any magnetic field you have on that ribbon, you let a flux go through the ribbon, and you increase it by one quantum of flux. And as you do that, Loftin tells you that the ribbon has two rings, and the left and the right ring, and a certain charge is transferred from the left ring to the right ring, and the charge that has been transported is an integer whenever you an integer, always the same integer if you repeat the experiment, provided the flux you measured in addition is a quantum of flux. And based on that, we want to pick up with something that is manifesting. Okay, so here is the idea of the ribbon. So you put this ribbon onto the plane, and then it becomes an annulus. And then you shrink the inner rim of the annulus down to a point, and you send the outer rim of the annulus out to infinity, and then you're left with this puncture plane. And with the puncture in the middle, you have this flux that you steadily increase. From 0 to at first some value phi, and then we in particular choose this value phi to be a quantum of flux. And as long as you do that, some charge is to flow in or out, and it's going to cross that certain C that is. We want to understand how to quantify that thing. Before writing the next formula, let me say what the idea is. There is this flux that comes out there from the screen. on the screen and is changing in time. Then Faraday, remember Faraday's law of electrodynamics, tells you that there is an electromotive force around that flux. So there is an electric field which at every point of the circle points in the direction of the tangential vector ds, or maybe the opposite side, because here I do it like this, anyway, like this, maybe it's the opposite. And then, by the quantum Hall effect, a current should flow perpendicular to the red arrow, which is in a radial direction. That is in the direction of dn. That is, it flows out, or perhaps in, if the sign is opposite. Okay, so let's compute that. So how much charge flows through the circle by unit time, dq by dt, when we integrate the current density across the circle, that is, you take the normal to the circle again, and if you count the charge positively when it goes inwards, then you put the minus sign. Then there is this quantum Hall law, which says that J is proportional to E, the proportionality between sigma H, but also perpendicular, and that is taken into account by replacing the dn here by the ds, the tangential. Now here you recognize the electromotive force together with the minus sign from the Lenz law, if you want. This is d phi by dt. So if you integrate this over some time span t, then you end up that the charge transported in the meantime is sigma h times the flux. And so if the flux is one quantum, let me just anticipate this, 2 pi, then you should get a charge transfer which is 2 pi sigma h, which is the quantity that's supposed to be quantized. Now let's understand how this comes about. So if the flux is generated, so let me say this. If anyway you have a magnetic field that you need in order to have the quantum Hall, and that's all over the place. I'm not talking about that. I'm not talking specifically about the additional flux that has been placed. Let's assume that this flux is generated by a gauge potential, comes from gauge potential. If you were to integrate this gauge potential around that circle here, well, what is this? By Stokes, you could integrate something over to this, that would be the curl of A, that is the magnetic field, and the magnetic field contributed by that flux is the flux phi d. And a solution to this equation, that is NA, that would provide this, is given here. And seemingly it is written as a grade. It's the gradient of this function that you see here. It's called chi. Indeed, if you integrate the gradient along the circle, then you just get the value at the beginning minus the value at the end, and the argument has increased by 2 pi, so then it's just phi. But this is nonsense, because this function chi should be a single valued function, which it manifestly isn't. When you do the circle, the argument increases by 2 pi, and we return at the same point, and there should be just one value. So I've cheated you. But nevertheless, let's cautiously go on, nevertheless, and just say if chi were single value. Chi were single value, that would be a pure gauge, and indeed, then you would have no flux at all. It would not generate any magnetic field at all. But now suppose the A is still 0, right? In one gauge it is 0, and then you have the Hamilton, there's some Hamilton in HB which goes to E. But that is supposed to be equivalent, is the kind of single value, to this choice of gauge. And as we saw before, to this, the Hamilton corresponding platform is not HB, but that conjugated by U, where U is this multiplication operator, e to the I pi of x. That is a unit. Now, this thing here is not single value, just as chi is not single value. with one exception though. If phi is equal to 2 pi, then this kite is not single-bodied. The thing increases by, you know, this is 1, but yeah, it still increases by 2 pi. However, U becomes single-bodied because U e to the I 2 pi is again 1. So despite that no flux and flux 2 pi are physically different situations, the two situations are unitarily conjugated by this U, which is e to the I. Let me write it also for later. U equal I, the argument of x. Then chi and phi is equal to pi is just argument of x. That is the thing that does the unitary conjugation when the flux is a quantum of x. Okay, so now with that we try to come up with an idea for a definition of the whole. So here are a few further notions are needed. I think we saw it before. There is the Fermi energy, which says that all single particle eigenstates of the Hamiltonian that have eigenvalues of homogeneous energy spectrum, whatever, below you are object. And there is a formula for it, and let me write this down when the flux is still 0. That's just spectral projection of the Hamiltonian that corresponding to the interval of energy ranging from -infinity all the way up. Yeah. And then the Hamiltonian with the quantum of flux is unitarily conjugated. And likewise, the Fermi projection for the flux to pi, the quantum of flux, is likewise unitarily conjugated. So that will be the corresponding Fermi projection. That is the situation you have at equilibrium when there is a quantum of flux. But now we actually do something different. There is no flux at the beginning, and we steadily increase it towards the end. And then, so the flux is a function of time, which increases from 0 to 2 pi. And what is the state in single particle density matrix as we perceive? Well, we have to solve the Schrödinger equation, the time-dependent Schrödinger equation, and that gives rise to a propagator, which has a dependence on t, which has been suppressed. It's called here ut of t. But we are interested in the final time when the flux 2 pi has been reached, and then the state so obtained is obtained by this conjugation here, from p, by u tilde, not by u. That's a different thing. That's just the final state we get. It's not the equilibrium state that we would have if the flux had been at the value 2 pi since then. But this offers the possibility of coming up with a definition, and the tentative charge is how much charge there is in our final state after pumping up with by 2 pi, as compared to how much charge there is in equilibrium if that flux had always been there. So this formula is somewhat cryptic. It comes in quotation marks. So what is first the idea of the dimension of a projection? That's the dimension of its range. So the PU stands for, the original PU stands for a Fermi, and it contains infinitely many states because, the plane is infinite. That one likewise contains infinitely many states. So this dimension here is infinite, as it is written there. This dimension here is also infinite. And we are trying to, out of these two infinities, to find a sensible manner to take the right difference. That is the task. And then, once this task is achieved, it is based on this argument from the slide before, will be the transfer charge, and therefore 2 pi sigma. Hopefully this. And so it will be. Now, the first thing that we can do is to replace this u tilde by just 1. How come? This u tilde progresses with time. T, and then there is a final time. But it changes continuously. And so if you have a projection and that changes continuously, then its dimension doesn't change. Now, of course, this dimension is now infinite. But if you add it to take a little bit of place, you can still say this dimension of that projection, which has been obtained by a continuous deformation from the original one, is still the same. So we can write the dimension of the original Fermi projection. And what we have to subtract is, as just before, that of the Fermi projection once the flux to pi is in place. And the right notion there comes from the index of a pair of projections. Something that was already looked at by Graf, but there were sort of people like that on side and side. And the prototype for this idea is Hilbert-Sotten. So Hilbert, you know the story of Hilbert-Sotten, or everybody knows. If not, okay. And here it comes in this in guise of this Hilbert space, L2 of Z. We saw it last time, so that's the request. I'm not going to repeat it. In any event, the basis vectors of this infinite Hilbert space are indexed by the integers. And so each of these dots, never mind whether empty or full, stands for one basis vector in the space and for C. And then you have projections P that is spanned by these basis vectors there. And another one, another projection Q that is spanned by this other basis vectors. And both define infinite dimensional subspaces, infinite dimensional projections, and somehow we would like to count the dimension of P, that is the dimension of the range of P. Okay. The dimension of P, which is infinite, and the dimension of Q, and subtract. Now notice that for a finite dimensional projection, dimension is the same as the trace, because you write that down in the basis of which the first dimension P basis vectors are inside P and the remaining one are outside. So when computing the trace, you just compute as many ones as the dimension. And so this could be the trace of P minus the trace of Q or the trace of the width, which seems to be a clever thing to do, because even though the trace of the individual is infinite, if you first take the difference, then you easily see that only this guy here is left, and that's a rank 1 projection, and that will be decided. Let me extend this a little bit. More generally, the formal definition of the index of a pair of projection goes like this. Provided it is well defined at the end. So here you have your projections, the index thereof is this. You first look at subspace so it's a subspace of the range of P, as you can see, consisting of those vectors that are fully orthogonal to Q. And from that you subtract the fields also Q and P change. So if you look at it here, so the range of P is spanned by the rect basis vectors, and among them there's just one that for which the projection onto Q is 0, and that's the first one here. And when you count the second dimension, well, everything that is in the range of Q is also in the range of P, so that second dimension is. And that formula gives 1 minus 0, which is again the answer that you'd like to. So the example, both generalization, this one, that one, gives the dimension 1. And in the application, we shall now see the more effect. Only this index is sophisticated enough to find the answer. And this is still problem. Not all ways of counting difference of infinities are as good as they are. Okay, so here are some properties of the index. It's additive. If you have P pairs, one is PQ and the PR are Q. The thing is additive on a slide backwards that I'm making here. And And if the two projections are very close to one another, then the index of their differences. This, in hindsight, is a little justification of my move I made before when I said, well, there is this unitary which brings us from the initial fantasy to whatever final state we get at the end. But since this is continuous, I can split it up in various little steps, and for each step, the corresponding projection is still different by little, so the index hasn't changed, and then by the additivity, I can go all the way to the end. And so that looks, in hindsight, would be the legitimate move. And then we saw that if P minus Q has a trace, then the answer should have been that index. But sometimes P minus Q is not trace class, but some power of it is trace class, or then P minus Q itself is in some trace idea, as they say. Now here is a question that are you familiar with trace class, trace ideas, or not so much? Maybe not. So let me just say some very cursory words. If you deal with finite dimensional vector space, then every linear map, drop a map from the space to itself, every linear map or every matrix has a trace. But if you go to infinite dimensional spaces, namely Hilbert spaces, then not every operator has the identity wouldn't have a trace because it would have some infinitely many one. And so somehow this is a vague similarities like with series that you learn in calculus 1. Not all series are summable. And of course, some series that are summable are those that are zero after a certain point. It's like finite series. And there are also a few others which are summable, but the entries have to decay pretty rapidly after some point. And so somehow place class operators, you can think of them as just at first finite rank operators that simply project just from a finite dimensional subspace, and then in place is still defined. And then there are a few more that you can approximate by those, like you can approximate sufficiently fast decaying, a series with sufficiently fast decaying entries by those of finite lengths. That is sort of the half idea what the place class often is. And sometimes only, certain the series by decaying like 1 over n is not summable, but if you square it to the power 2 or 3, it will be. And this operator, if you take some power, then maybe it may become place class, even though at the beginning it was. Okay, and so let me go through the first two remarks. Only if P and Q are finite dimension, then the index is indeed just the difference of dimensions, as it is stood by now. And so here for this index, there can be various formulas because you can make various choices of it. And so if something is already place class, then its third power will also be in place class. If a series like 1 over n squared is summable, then if we raise it to the third power, is still summable. Right? And what is not, but with the series, it wouldn't give you the same sum. But in this case, it gives it the same sum. The trace of P minus Q cubed is the same as trace of P minus Q. And here is why. If you look at the difference and you do some manipulation, you can write it as a double commutator. But let's focus on the outer commutator. So it's a commutator. And P minus Q being already trace class, that inner commutator is trace class. So as a result, let's keep that on hold. And here is another remark that if you know that two operators, possibly individually not even place class, but in their product being place class, no matter the order, A, B, and A, then you can pretend that trace is cyclic, and you get that for the trace of the commutator, and you get zeros. And this hypothesis here is now satisfied there, and so the trace of this double commutator is going to be 0, which explains why this is independent of n as soon as n is large enough, so that expression is the last remark of this. I think also here we have one more remark. So here this prompts a definition. So this, based on this Laughlin argument and the index of a pair of projection, we might say that the transfer charge by increasing the flux and therefore 2 pi sigma p is given by the index of 2 projections. Namely, once the Fermi projections in absence of additional flux, then the Fermi projection in presence of an additional quantum, which is unitarily conjugated over by the sigma. This goes back to the Nisar, and then there's been rediscussed in some different language by Arbor and others. And they notice that it takes, it writes it as a base of the difference, provided the power is, it has to be off, as in general, but it is Theo. Here is again the U, which is the, it can also be written as the base of the complex number. So if you can look at this point either as an X or either as a complex number. Okay, and indeed the second remark is that this difference upon closer inspection is not raised class, but its power is. And the next topic would be, so the thing has been defined, then we may wonder how and whether we can relate it to the bulk. So then we also necessitate at first the definition, but let me first remind you what it was in intuitive terms. So if you have no electric field, then at least in some model, electrons run classically run on a circle and they don't move on average. They don't drift in the long term. But if you apply an electric field, then the drift current comes up. And that is called J. This is weak and proportional. And you would like to know what the coefficient of proportionality is. That would be the whole conductance in its bulk understanding. And here is a formula what can come up with. The formula has not yet, ingredients haven't been explained yet, and they will do it. So it's again a double commutator. And what do we see here? P mu is the Fermi projection as before, no change. But then there are these lambda 1 and lambda 2. These are switch functions, but first let's look at what the switch function is without any subscript. So that's a function of one single real variable x, and it interpolates between 0 and 1. That's all it does. Switches between 0 and 1. And when it comes with an index, could be 1 and 2, then it's a function on the plane, and it's just a switch function evaluated on the first coordinate or on the second. Okay, so then this is the formula. I'm not going to justify this in detail as the one before, but let me just say some remark which might come up later. This generalizes an earlier formula that essentially goes back to Paulus and is, however, applicable only in the periodic case. When the material is periodic and there is a thing as a Brillouin zone. We'll see these topics a little bit later, but you may know them already. And then the Fermi projection can be decomposed according to each and every value of the quasi-momentum K. And then instead of having these commutating switch functions, you would have derivatives of this P of K with respect to either the first or the second component of the quasi-momentum system. And then this mysterious expression here on the right side, up to a factor of, if multiplied by 2 pi, turns out to be the Chern number of a certain vector bundle over that torus vector 1 that is defined by the range of these projections Q. Maybe this is already all familiar with you. Good. If not, we will revise this down. But for now, we come back, we leave the periodic case again, and we come back to this formula, and it's not needed. And it pays to just think formula is well defined. And what relation it has with the original Cooper form, with the Cooper formula, which just is the coefficient, the relation of proportionality between the current, say in the one direction, and the electric field in the perpendicular direction, which would be the two direction. And then you may ask, well, why? No, how the heck do you get the switch function? They have a physical origin. We would like to measure how much current there is. I should use this one. How much current is at least that is flowing in the one direction. Okay. How much is flowing across this distribution line? Actually, not the total current, but the current density. But never mind, this distribution line is the following. It defines the following. It separates the charge on the right, which counts as 1 by the switch function, from the charge on the left, which is not counted because it counts 0. So lambda 1 counts the charge on the right. And this commutator, Mr. Hamiltonian, is the current across this fiducial line. So that's the physical origin of having the switch function lambda 1. And then this current would be infinite if the electric field were everywhere, but if the electric field is present only vertically, but only in the blue region, well, then it would have a potential that is, say, 1 here and 0 there, which is again a switch function. So the electric field would be minus the gradient of lambda 2. And so the current that flows when you have a potential drop of just 1, like the switch function has, then it would be the current across the ceiling, equal because the current density. So both lambda 1 and lambda 2 have a physical origin by which they appear in finally after some manipulations. And the other thing is, why is this well defined? So roughly, I told you that an operator has a well-defined place if it acts non-trivially order and finitely many lattice. So suppose there is a lattice here, and there are lattice points, and therefore vectors associated states in the Hilbert space associated all over the localized here, there. So things will all contribute to the place, but factually only there a few. And how does it, which one do? Well, suppose that lambda 1 were not the switch function, but were constant, like the identity, like the function 1, therefore the identity operator, then this commutator would be 0. And so you realize that contributing to these states on which this clean operator acts substantially are only those where lambda 1 is not constant. The lambda 1 is constantly 1 or constantly 0, it's irrelevant. And only the clean ones out of the states localized here in the green region are important. And likewise for the other one in the blue region, and since you have the product of both, it's the kind of commutator to begin with the product, it's only those in the intersection that matter. And so in the intersection, you only have finite linear states, and it's reasonable to expect that the space is fine. So that's as a motivation for this definition. And then you may wonder whether the two definitions we now have at our disposal are the same or not. And the answer is yes. There has been a first result already quite some time ago, which was placed in the setting of a God component. So things all become random, and the probability space becomes important. In fact, sigma Hall and so on is defined as an average over the probability space. Something we may wish to have or may not wish. In any event, if you do accept this, and particularly if you allow for a mobility gap, then the longitudinal logicity of this conductor is 0 for mu with lying in mobility gap, as the physical law predicts. And moreover, and more importantly, the definition I gave before with the pair of projections of the Larkin pump, the one suggested by the Larkin pump, takes the very same value as the one suggested by the Cooper form. Proof is by non-commutative geometry, and then Adler and Simon return to that and prove it even without the probabilistic setting. And in a sense, the statement is the same, just spelled out. Here, sigma p, that is spelled out as the index of the pair of projections, written like this. And here you see again the Cooper form. Now, I know that some of you are interested in work on this kind of things. So at first I thought of giving the proof, but time is quite advanced. I think I should move to a break. And I will not give the proof, but I will give you the core of the it's completely non-understandable how we get the core. But the core of the proof has nothing to do with physics anymore. It has to do with geometry. In particular, you see no trace of this Fermi projection. Fermi projection was present. It's present. No, I'm not going to break. I'm going to lose time. I'm going to do nonsense anyway. Well, you know. Okay. If you remember, the Fermi projection was present 3 times on the left and 3 times on the right. 3 times on the left because there was a third power, and 3 times on the right because it was a book. And the 3 reflects in triangles. So here you see a triangle, X, Y, and Z. The Fermi projection itself has disappeared. And here you see a generic point P in the plane. And I'm asking you to do this. Stand in P and determine the angle of view that there is between X and Y. So that angle, that first angle. And then the one between Y and Z, the angle, that of sine. And then finally the angle between Z and X. And these 3 angles are written. The angle of between X and Y is viewed from P. And likewise for the other. Don't take these angles, but take the sines thereof. Sines thereof. And integrate the result over all the plane. And the plane is that this is a formula for the area of the triangle. A formula that has been discovered by Chern. Trigonometry was known since antiquity, but this formula was. How come this formula like that? First, let me give you a round thing, which gives you also a round result. Split this integral in 3 parts. Each step for the sum, each one. So just look at the integral of the first. So forget Z. You just need X and Y. And so there is a certain angle of view here for this point P. But there is another P, the one mirror reflected across the segment XY, where the angle of view is opposite. And the sine is likewise opposite because the sine is an odd function. So there is a compensation by the contribution from P and the contribution from its mirror point. That must be 0. Must be 0 for the first integral and 0 for the other integrals. Did you catch this thing? Okay, we'll catch it at the end. But here's the proof. Let's first drop the sign. The claim it's true even without the sign. It's only for sign or for other anticipated function. That's exactly the key to the proof. And you must have thought of proof by now. I was the. That's the observation that's also. So let's drop the sign. And then, for this point P, you see that the contribution is 0. Right? But if that point P had been inside, then, as we know, the sum of the angles sums to 2 pi. And so this is the whole round bracket is 2 pi P's inside and 0 outside. So you're just integrating the characteristic function of the characteristic function of the triangle times 2 pi. Well, that's 2 pi times the. And now let F be odd, but that it behaves like you know, now we just move for the angle itself. That's the function t and the identity function, and that differs just to higher order, like the cube. For instance, the candidate for such an f would be the sun. It begins like t, but it differs from it. For small r, it is like t, but then it differs the cubic order. And then I claim that if you just look at the difference between the two f of the angle minus the angle itself, and that just for one of the terms, not for the sum of them, that would be z. And why would that be? Well, that is because of the reflection argument before. It still works because what was needed was the fact that it was odd, but now it is correct because the integral. So how does this angle go if you go far out? The angle goes like 1 over the distance, and 1 over the distance is not integrable in the plane. That was the mistake one before. But the cube thereof is integrable in the plane. So now the argument is okay. And so in order to do this, you see that you can first prove it for the angles, and then you see that you could also look at the difference with respect to the sign, but the difference to the sign would be 0, so it's also true for the sun. That is just understood. You must have this. And I think now it's time for the break. Yes.
Can you repeat again what the characteristics function of triangle?
Yes. So again, so here I'm dropping the sign, and that is the first. Then if P is outside of the triangle, then the sum of the angles is 0, as you can see from this case. But if P is inside, then you make a full turn and you get 2 pi. And so the whole function that you see here just takes 2 values, 2 pi when you're inside and 0 when you're outside. So if the value had been not 2 pi but 1, then those would have been the characteristic function. Integrating characteristic function gives the area, and then there is this factor of 2 pi now. Another question? And let's have it.
Yeah. Okay.
I just realized it was CD part is long. So, there was there's been a lot of comparison between 2 definitions that we made in Edge and bulk. Edge would still have formally. We skip all that. And let's go to the periodic setting. Hopefully to be able to also describe some topological insulators that have some symmetry, like time reversal invariance. Okay, and as a preliminary to the periodic case, I need the notion. But if you tell me, you all know vector bonds inside out, just a bit. No.
Without the inside out.
No. That's not. I'm sorry.
Maybe
I'm sorry. Just the base. So I try to go a little bit fast, but you're most welcome to slow. So at first, you have the notion of a differential manifold. Locally, they should be known. And informally, a vector bond is then patterned after a Cartesian product M, Cartesian product, some vector space M. So M manifold and vector. And this is something that is true locally, just as but the F is R N is only true. that's sort of the idea that they do. And so here is a slightly, proceeding by degree. Here you have a manifold, and if you just look at the piece of it, that's some neighborhood U, then there you can say it looks a little bit like a piece of Rn, and that you can cover the manifold by local charts. And likewise, you can do something with the vector bundle that is called E here, so that's the big space here, but it sort of has inside the base space N, this manifold N. And so the two are related, just like, at home, you have a comb, and there is a shaft, and there are teeth. And so a vector bundle is a little bit like a comb. So there is the shaft in the role of the manifold N, and over each point of the shaft, you have a teeth, which is a vector space. That is the idea. And so locally, it looks a little bit just like a Cartesian product of this open neighborhood or neighborhood inside N. Cartesian product is. There is a map here which to every point in middle projects it down to the point in P over which it is. So the projection that goes down along the tools. And so here is probably a somewhat more formal definition here of complex vector bundle. E for short consists of therefore a map I, that's the canonical map, that projects the vector bundle down to the manifold M, and the map pi is the differential map between these two manifolds. And then you can look at the inverse image or the image of every point P in the base space, that's the tools over it. That's called EP, and that is supposed to be a vector space. And so if you just restrict this to restrict yourself to a neighborhood U there and look at the inverse image there, and it's diffeomorphic to U times F. And for by this, when you look at the single point P and just look at the image of that we said that has to be in a vector space, and it's just, you get such a relation just by restricting the one before, and after restriction, this becomes a vector space. This F is a vector space, and therefore outside is really a vector space. And this is supposed to be one also by definition. And there is some nomenclature that goes with it. Is the total space, N the base space, F is the fiber, and collection of neighborhoods U with these maps phi. So a single U and a single map phi is a boundary chart, and then there is the notion of the rank of the vector bundle. That's not the dimension of the vector bundle as a differential manifold. It rather is the dimension of the typical fiber. Good. So now the vector bundle, we said that the vector bundle locally over a certain neighborhood U always looks like a Cartesian product, the second factor of which is the D. But we say that the vector is real if this holds global. This is true all over the place. It's an important notion. And so, what we said before, bundle charts be local, not global. And here is an example, a visual example that we say. So it's about a line bundle that is a vector space of rank 1, and the typical fiber you can just take it as the vector space of the bundles. The base space is a circle, and the whole total space is a Möbius strip. We should think of it as infinite Möbius through lines extend forever. But when you pick a non-zero vector over one point of the circle, like this, and continuously move it around, to the initial point, well, you end up on the other side of the diagram. So it is not a Cartesian product globally, it is a Cartesian product only local. To look at every piece of it, it looks like, but it's not so. So that's the interesting first example of a non-trivial vector. It is the second one. So you take the sphere, and at each point, you take the tangent space, and in this case, the typical fiber would be R2. And so the question, if this were a median, what this would mean? That you can find coordinates basically on the sphere such that the induced coordinates on each tangent party are those you see here. And you know that this is not possible because when you try to put coordinates on the sphere, longitudes and latitudes, you see that the meridians, cross at the North Pole and the South Pole. There's no way to avoid them. So again, this is a rough explanation why the tangent part of the sphere is a non-trivial vector. The interesting thing is that now they come up also in solid state. So you might read this little notion here. So a section, so here is again the picture of the base space, a fiber, a total space, and the section is a smooth map. So a global section, let's say, is a smooth map that associates to every point of the base space a choice of a vector in the corresponding fiber, EP. That's it. And so another way to say it is that if you at any point you first take the S and then project back, you end up just down there where you start. So this is the idea. Section could also be non-global if this is through or made with view of the first step. So I started again. I should close at 3:45, right? Okay. And so let's come to the other segment more. So we should take as the position space the plane or a lattice, as I said before, and then there is a group of translation. So you can translate in one direction, you can translate in another direction. That's a discrete group. So there is essentially this group is C. The C group. And you can translate by a vector N, which has components in one of the one of them. And so it brings your point X by a vector N. And so then you have all the possible translations, and then you have a unit set. Or abstract, you say that you may identify points that fit by a lattice vector, but that is just like picking one representative for each class, and then you end up. And now this is an abelian group. So it's nice to think of its representations, but all the reduced representations are therefore one-dimensional, and they are the same as the characters. So what are the characters that are abelian? Now, sorry for this change of notation up there. One of the two points of the single page. And now M1 and M2 are vectors for the nodes. This hat. And what it means is this, that if you a character or one-dimensional representation evaluated on the sum in the group gives the product of the representations. And that's again a group. And the way that this is represented in physics is not by calling it chi, what chi is, but by saying that this map is written as e to the minus I k. So the bounded solution of this equation out of this form for some k, which however is not unique, because if I change k by 2 pi, so for any component of k by 2 pi, then this thing doesn't change because A has components that are integers. And so it's the plane R2. Once you identify points that differ by 2 pi magnitude, that is a torus, and it is called the real zone. And this k there is called the quasi-momentum, and is defined modulo 2 pi in each component. So far, so good. So if you already know the definition of things, so because you live, that's where don't change it in your mind, your system. Then we have a Hilbert space, which is first the Hilbert space of functions on the plane, and on there, or you may add some term is freedom intensity by Cn, not a big deal. And then the wave functions may be translated so that Hilbert space carries a representation of our abelian group of translations, and each translation vector n is represented by a unitary operator on the space. And you can decompose the Hilbert space according to the different irreducible, as the mathematician would say, or according to different quasi-momenta, as physicists say. And how does it go? Well, you have this the representation of the translation group on the Hilbert space, and you just decompose it into irreducible, one for each character, therefore one for each k, as long as it fits on the torus. And on each subspace, it's just multiplication by the character, e to the minus I k. So that's the reduction of the representation. The composition of any psi into lots of psi k of x is just given here. It's sort of weird decomposition. And by this, the wave function psi in the Hilbert space is represented by a bunch of psi k's, one for each k, for each quasi-momentum k. And so that the right-hand side, the elements of this right-hand side are the elements of this direct integral. What is little h there? That's just L2 of the unit cell, because the wave function that corresponds to the irreducible subspace of character k is defined, is fully defined by its value itself, because as you move it along, if the values it takes, as you explore other regions or cells, it just changes by this factor is a translation. So the fibers of this direct integral are just L2 solid, or have I identified as L2 solid. What does it say there? So technically speaking, the state, which is a map from k to psi k, as we said, is, in other words, a section of the Friedel vector bundle given by the base space P and by the fiber L2 of C. And then you have a Hamiltonian that is also supposed to be periodic. That's the whole business. And therefore, it also decomposes with respect to each irreducible representation, and therefore it acts on each fiber psi k within the fiber by an operator that we shall call h of k. And so h of k acts on the typical fiber, which is a unit cell, and it is a bit like a Laplacian on a now finite domain, unit cell, no longer infinite space, and so you would expect that does have discrete spectrum rather than continuous spectrum, because C is a compact set, and it does. And let's just label the eigenvalues of this by epsilon 0, 1, and so on. So they depend on parameters. And here's the picture. So here's the torus on the down at the base, and every point K, so it's the torus with the opposite side identified, and each point K has two components, K1 and 2. The point is here, and above here there are just discrete eigenvalues. If there are more, if you're in the lattice, they're just fine. If you're in the continuum, and the spectrum of the whole operator is the union of all these discrete spectra. And that union no longer is discrete, but is continuous, because these discrete eigenvalues, they vary as K back. So to get the picture, if you just, maybe I should have said the word here, how do we collect all the values, all the pink lines? Well, we project all their values to the vertical axis, and we can do this in 2 steps. First, we just project the weight K2, and then we still have a function of K1, and then it already will look continuous. So here we collect all the some of the discrete eigenvalues for different K2, and here again, but it's still separated, at least in this example, by a gap. But then we can also project in the remaining direction K1, and then we get intervals and gaps, which are now here related from. So that's the typical spectrum you get for a different bands and gaps. And now let me explain what the Fermi boundary is. So there is the spectral projection P that is associated to a part of the spectrum separated. So typically, the Fermi projection, everything below the Fermi energy in the gap, as we've seen before. So that part of the spectrum, black, is separated from the right one by a gap. But you could also just turn your attention to a single band, as long as it is separated. That would be okay. And then we saw that the Hamiltonian decomposes, and this being a spectral projection of the Hamiltonian, it decomposes as well. So that's fiber is GK. And it's still a projection to each fiber. And so it's so each fiber has as its fiber space, this space dot gauge. And the range of this projection is a subspace of this dot gauge. But dot gauge was sort of the same all over the place. The boundary was here. Maybe I could say that. Did I say that? Or should I say? So this boundary, it's something missing. So the top, no, it's not an estimate. It was the, let me properly precise. The vector boundary we have here is the T cross H, and therefore it's even. Because it's a Cartesian product. Yes,
how do you know that the whole H?
You may in sensitive class. What the fibers here we are. So let me call it what so the whole bond is called what they like point B not because of good. If that's the type case element to that file, then it means it's K positive K out. So K of X minus K. And be such translation to the minus type K. So the knowledge of that on the unit say is sufficient to determine the whole thing. And so the value of function unit set determines the sign K and can be taken as an idealization. And therefore, we have a idealization that's for all K, it's a global idealization. There is this little detail which shows that there's a trivial dot. This provides the psi k restriction, psi k in itself, which then as an element is in this L2 of the unit cell that provides the global trivialization. But there is no reason to go home on action. It's not a game over. Because the main point is that we are interested in the sub-bundle of that bundle defined by in each fiber having a particular subspace. And while the whole thing is trivial, the sub-bundle did not do. In fact, you know, this is something that solid state physicists have known since ever since, because Bloch theory goes back to the 20s, but it wasn't till the year 2000 or so, or like, no, maybe it was a little bit below the 90s, late 80s, that people realized that these bundles might be non-trivial, and that there is interesting geometry that comes from the top. Something that for 60 years escaped their radar. And now we still have 15 minutes, so maybe that's good enough to tell you about how to identify the non-triviality of complex vector bundles on the two poles. That is what the point is all about. So here we have the two poles, and unfortunately the points are not called K, was it was before phi, corresponding with the coordinates of phi 1 and phi 2. And you know, like physicists do, they like to think that the creosome is 2 pi long, and so the points at the corners have these coordinates. So this pi is the other coordinate, and these dashes here, they mean that opposite sides have to be identified. Stops. And you can think of the fibers as being abstract vector spaces placed over these points phi. And there are frames. So what are frames first? So in each fiber, this fiber E5, we can look at the basis. So if this has dimension n, then we take n linearly independent vectors, V1 through Vn, collectively call the basis E. So, and the frame bundle is also a bundle over that same torus here, but there's different fibers. And the fibers over a point phi consist of all possible bases that you may have in E5. So before, you have a base space, and over each point, you have a vector space. You have all possible vectors, and now over each point, you have all possible bases. That's all there is. And so one question is whether this frame bundle admits a global section. That you can pick a frame, that if you pick it here, and then it's not too difficult to extend it over the whole square, that the task is whether you can glue it continuously across what is drawn here as a cut and come back to the other side of the poles. That is less obvious. So in fact, the thing is that the frame bundle admits a global section even though if the original bundle E is real. You can sort of understand it because if you can choose the frame a frame all over the place continuously, then you can use this frame to assign to every vector coordinates, and the fiber becomes Cn. And so you trivialize it all over. So this leads us to the Chern number. So first, you see here, I've cut the torus I had before. So instead of, here you see the gluing signs, but here I have a cut. So the picture of it is now that it is a cylinder. It's open at two sides, but still a circle in the other direction. And here is a little lemma. On the cut toes, you can still find a global frame of a global section of the frame bar. So over each phi, there is a basis in phi for that particular fiber. But as you move the point across the circle here, and you can continue to frame that in such a way that you combine. I'm not going to prove that, but the real issue is when you try to do it, when you try to do the glue across to this, the gluing across to the cut they've made. That's the real challenge. And so what you now get is this. If you go to this rim of the cut, particularly to this point, in the fiber above that point, you have a basis because you come from this side. That shall be called the basis of frame P plus at height phi P. It's just one coordinate because the phi 1 coordinate is I. It's not. But you may come to that end of the cut, which originally was the same point, but now you get another frame in the same space. The fiber is just one. And that's V minus phi Q. And just for convenience, I depicted the same basis here, also on that side here, just face to face to the other one. And so the question is, well, how are they related? Here's something you can always say. If you have one vector space and two bases, they're always related by an invertible linear transformation. And so this can be written as a right multiplication of V minus. So V minus was a vector of vectors. We would write V, the whole basis, as a collection of n vectors, vectors, and if you linearly combine them as by right multiplication with a matrix, you get new vectors, and if this matrix is invertible, then you get the new basis, and vice versa. If both are bases, then this matrix of transformation of the basis is invertible. You have one for each point phi 2. So if phi 2 runs over that cut, which in itself is a circle. And so here's a definition. The Chern number of the vector, one of the possible definitions, not the one we find most, but the Chern number of this vector bundle E is the winding number of the determinant of the matrix T of phi 2 when you run along this circle. Here, it might have a winding number, and that's the Chern number. You see, if the thing were treated, then you could arrange, if the original bundle were treated, then you could arrange the frames on both sides of the cut so as to be identical. But then T would be 1. And the determinant of T would be 1, and its winding number would be 0. So you know what to do here is this is the cut. You have the winding of phi 2. As a function of this phi 2, you go to the determinant of phi 2, and that's the complex plane. The origin is avoided because the matrix is vertical, and it does something, and it does this. So I think we can come to the right as a term once in this direction, term -1, that one, which has that one which out. So no matter what you want to call this thing, this you see it measures an obstruction because if the thing were treated, that thing would have to be 0. If it is not, then we have an obstruction. And here is a way to visualize this. So for each T of phi 2, you have an invertible matrix. So it has eigenvalues that are non-zero. And you follow their phases with phi 2. when phi2 runs over the circle. And so here is depicted, it's a, for each phi2 runs on the horizontal, and for each value of phi2 you have a circle, therefore you have a cylinder, which has nothing to do with the cylinder. But if phi2 is 0, just here, you have say 3 eigenvalues. If phi2 moves, these eigenvalues move. And then to detect the winding number of the geometry, we draw a function line like the ones there, and you count the crossings, and you pay attention whether the crossing is in the clockwise, counterclockwise direction. So you see here 2 crossings, and if you check the sign, there would be -2 crossings. So the Chern number of a bundle that provides eigenvalues like for a transition matrix like this one would have Chern number minus. Okay, so the bulk index is the Chern number of the Fermi bundle defined by the Fermi project. The physical meaning, which Towers has discovered, is that sigma h up the whole conductors of the factor of pi. It is quantized because the Chern numbers. There is a remark that this same Chern number, which has been determined by looking at the gluing from the cylinder back to the torus, could also be completed by integral over the torus by the expression we saw before, but by now I think that all the integers of this formula have been expressed. In this sense, it has more the meaning of certain curvature that I'm afraid of best. So I think this is what there's of course more that I would like to say about the periodic setting, but I think we leave it like this. I would have liked now to go on with finally symmetry protected topological insulators, namely, let's see how we get our doing. Okay, so yes, with time reversal invariant topological insulators. So I think we should stop it in 2 minutes or so. I will do it tomorrow. Oh, that's another portion for tomorrow. Let me just give some basic things in this. So, what is time reversal for all about? So again, first for topological insulator. This slide appeared. They're insulated in bulk or in pentatons with respect to data Fermi energy. Is this idea of topology that you can perform things, but some quantities, like this Chern number from just before, do not change while the perform these quantities, as long as you keep the gap on. So if you start to if you start closing the gap, then the very Fermi bundle which I defined no longer exists because it doesn't have a constant. The fibers don't have a constant dimension anymore, so it doesn't qualify as a vector bundle. So the fact that it's an insulator manifests itself in the very existence of the vector bundle. So that's the situation we had. But now we have this time reversal as a symmetry that comes on top. In fact, it's a periodic time reversal. And what does this? So there is a map theta on the total Hilbert space called time reversal that is anti-unitary. That's the way time reversal is implemented in quantum mechanics. And it squares in principle to +1 and -1. And they say fermionic means that it squares to -1. And it should be a symmetry of the Hamiltonian, therefore it should convene with the Hamiltonian. And in the periodic case, what does it like h, theta should commute with the last question, right? And then it means this, that it's not that it commutes with h of k, but that if you conjugate h of k with time with diversion, you get h of -k. There's something to do how that's been based. if you have a wave function is positive, you know, this k, there's a behavior like equal like kn minus like kn translation, when that flips into something like that. So that's why k goes to minus. So that is the situation, and so you still have a vector bundle as we had before, but with an additional structure with a map theta that maps the fiber over k to the fiber over minus. That's called the time reversal bundle, shorted, you know, by this thing. Now here's a remark. The bundle as such, it's so fibers are swapped, but in total, the bundle stays the same. That's the time reversal imbalance. But when you have a bundle, and in general, a theta which is not the same, the Chern number of that one is the opposite of the Chern number of the region. So if theta is E, then the Chern number is equal to its opposite, and therefore C. So these time reversal invariant points are trivial from the quantum Hall perspective of the game, but they are interesting. So they're trivial from the quantum Hall point of view, but they're interesting in their own class. As I alluded before, so from the quantum Hall effect, you can all deform them into one another, but if you insist that even along the deformation time reversal invariance be kept, then maybe you cannot deform them into one another and separate classes are enough. And indeed what happens, I see it. So that is, and here is a theorem that goes back to Attia in the mathematical setting. It's been rediscovered in the context of solid state physics by KP for general vector bonds that are time reversal invariance or that in dimension 2, there is an index that takes the value plus or minus 1. That's what yeah. I think we leave it here, and then tomorrow I will tell you how this index can be understood in a way that is similar to the one that we understood today. And then we finally will move on to class 3 at the minor. So